Hello and welcome back to App for You. In this particular video, we are going to discuss a concept called polynomial curve fitting. This particular concept is something that we come across when we are introduced to machine learning. Just mentioning this, that the content of this presentation, the content in the slides, the images have been taken from the book Pattern Recognition and Machine Learning by Christopher M. Bishop. So I would suggest you guys to basically refer this book for a more deeper insight into the fundamental concepts of machine learning. It's a very well written book, and whatever contents we will be discussing are basically somewhere directly or indirectly being derived from this particular book. So without further delay, let us now quickly jump into the topic about what polynomial curve fitting actually is. So before we begin discussing about polynomial curve fitting, let us first of all introduce ourselves to the concept of pattern recognition, right? So the pattern recognition, this particular problem of searching for patterns in data, is very fundamental, right? And this has been existing since a very long time. So the problems for searching patterns in data is a fundamental one and has a long back successful history. There are certain examples in the past which basically shows how important pattern recognition actually is. For example, the extensive astronomical observation of Tycho Brahe in 16th century allowed Johannes Kepler to basically discover the empirical laws of planetary motion. So this is very clear that Tycho Brahe basically he had observed some astronomical observations, and based on those observations, now observations are nothing but patterns, based on those patterns Johannes Kepler was able to discover the empirical laws of planetary motion, which later on became the fundamental development of classical mechanics, right? So we can see how observing the pattern, how a pattern present can basically lead to several theories. On the example, they say that the discoveries of regularities in the atomic spectra, this played a very key role in the development and verification of quantum physics in the early 20th century. So again, the patterns that were observed in the atomic spectra, those again gave some insights, and which basically played a key role in the basically development and verification of quantum physics. Now we can see what this particular slide is mentioning is how important is pattern recognition for us, right? And there is a very close relation between pattern recognition and machine learning. So both are very closely related, and these particular examples are itself evident of the fact that how patterns present in the data were basically observed very carefully, and some meaningful insights were generated, and those basically led to development of several theories. So the field of pattern recognition is concerned with automatic discovery of regularities in data through the use of computer algorithms, and with the use of these regularities we will be taking actions such as classifications of the data into different categories, right? So we can see that the pattern recognition, once we are able to recognize the pattern present in a data by using some computer algorithms, later on that particular pattern basically can be used to take certain actions like performing classifications, right, on of classification of data into different categories. So this was a brief introduction to what pattern recognition actually is and how machine learning is very closely related to pattern recognition, because when a machine tries to learn, first of all what it has with it is data. Using the data, it will basically come up with certain patterns, and those patterns will then basically help them to perform some tasks like classification, right? So moving on to the next slide, what we have is, so let us see what basically a machine does. How does machine basically captures the patterns present in a data? We will refer this particular image here. So this particular image is nothing but we can just see it is a plot of a training data set of n equal to 10 points, right, shown in the blue circle. So just to make it very clear, you can see this is a 2D distribution. You can see here basically some certain points are present in this particular graph, and these points are randomly generated, right? So these points are randomly generated. You can see there are 10 points, 1 2 3 4 5 6 7 8 9 and 10. So they are basically distributed in this 2D space, right? These are the axes present, and they are present. Now in order to generate this data, what we used was the sin 2 pi x function. So we use this function sin 2 pi x to generate this data, and once we calculated the value of sin 2 pi x corresponding to each point, we then added some noise to the data. Why did we add noise? It was very simple. We used sin 2 pi x to generate the data. So suppose for these points we calculated the value of sin 2 pi x, and this was the data point, right? The point was here, 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 actually here, this was actually here, here, this was actually on this curve, this was actually on this curve, and this point was actually on this curve, right? Now once we added some noise to it, we can see there was some distortion, right? So this particular point moved away from the curve, either upside or downside. So this is why we introduced a noise, because we wanted some random distribution of the data. So we know that the data that we basically generated here was using a sin 2 pi x function, and once we use the sin 2 pi x function to generate the data, we then introduce some noise to it. Noise to it in the sense, after we introduce some noise, the point basically moved away from the curve, not much, but a slight away from the curve, but still we can see it still follows the pattern of the sin 2 pi x. Very closely follows the pattern of sin 2 pi x curve. Now what we have the data with us, so we basically have some data points, and this green graph is basically for us, because we know that we basically used sin 2 pi x to generate this data. What is our target? So you can see the green curve shows that the function sin 2 pi x was used to generate the data, but our goal is to predict the value of t for some new value of x without knowledge of the green curve. So remember, we have to basically predict, the goal is to predict the value of t for some new value of x without the knowledge of the green curve. So you have to assume that you don't have any knowledge of the green curve, and now suppose I choose a random point here, this point, this value of x. So what will be the value of t corresponding to it, right? So at what point here, either here, or whether the curve will basically be here, and this will be the value of t, or this will be the value of t. This is what you need to find out, right? So this is the objective, right? So in simple words, I repeat again, we basically have some data points, 10 data points present in this space, and we basically know that these points are generated by using the sin 2 pi x curve. But now we need to basically come up with a curve which will basically say that yes, this is the particular pattern that is being followed, or this curve, in the sense we just have to come up with a function which will basically be satisfying that by using which we can say that yes, this data points here are basically following a particular structure. Now how do we estimate the curve? Now suppose the curve can be like this also, this can be one of the curve, right? But you can see these data points are not basically following this structure, right? Because what is the structure that the data points are actually following? This sinusoidal curve, right? So which means that this cannot be the curve, right? And what if we have a curve like this? So we can see that even this is not very closely following the structure, the actual pattern that the data points are actually following, right? So we need to perform some calculations such that, and in the end we will be successful, our model will be successful in coming up with a curve which will be very closely related to this sine curve which was actually used for generation of these data points, right? So how do we do that? So we shall proceed rather informally and consider a simple approach based on curve fitting. So how do we do curve fitting? So remember, we have data points, and this sinusoidal curve is what we know that this is only for us. We just know that the data points that are generated in this space was using the sin 2 pi x function. But now our objective is that the model has to say yes, this is the pattern that the data points is actually following by generating its own curve. So what we do is basically we shall fit the data using this particular function, right? So this is basically equation, it's not function, I'm sorry. So this is a polynomial function of the form basically yx comma w, which is equal to w0 plus w1x plus w2x square plus so on till mth terms. So this is a polynomial function. So this is the polynomial functions of any forms, right? The general form of the polynomial is as follows. We write yx comma w is equal to w0 plus w1x plus w2x square, and this will go on till m, where m is basically the order of the polynomial. So the general function of the polynomial is equation 1.1, right? This basically shows how a polynomial expression is actually written, and we know that any graph or any curve that we generate or create is basically nothing but a function, right? We'll basically, now in this particular space x versus t, whatever function or whatever curve we create will be basically a function of x, isn't it? That will be a function of x. So it can be a linear function, a constant function, a quadratic function, or anything. So that is why we have a polynomial function here, and now using this polynomial functions we will basically be coming up with a graph, or graph in a sense a curve that will be very closely related to the green curve, right? So how do we do that? So considering this particular polynomial functions here, what are m m is basically the order of the polynomial, and the w0, w1, w2 and so on, the terms w here are actually the coefficients of the polynomial coefficients, right, of these particular functions, and these are collectively known as the vector w, right. So these are basically going to collectively form the vector w. Now one thing to note is that this particular polynomial function is non-linear in terms of x, isn't it? You can clearly see it is a non-linear function in terms of x, because we have the x power 1, x square till x power m terms, right. So it is non-linear in terms of x, non-linear functions of x, but it is a linear functions of the coefficients w. If you look it in terms of coefficient w, it is actually a linear functions, because you can see the power of w is always linear in nature. So it is basically a linear functions of the coefficients of w. So the same polynomial functions is actually a non-linear function if you look it in terms of x, but if you look it in terms of the coefficients, it is actually nothing but a linear function of the coefficients, right. So what did we see? We see that we are going to basically perform the curve fitting, right. We are basically going to perform the curve fitting. Why do we want to perform curve fitting? Because we want to know what is the pattern these data points are actually following. Remember, this is hidden. We just use this green line curve to generate the data points, and then added some noise to make it move away from the curve. Now the objective is basically, we know that this is the distribution that the data points are actually following, right, because the data points are generated by using this curve only. But now our machine doesn't know that. For our machine, what it has in front of is just the data points. The green curve is invisible for the model. The model doesn't have any idea about the green curve, but the model has to predict the green curve to give an estimate about, yes, what is the pattern that the data points are actually following. So that is the target, right. So remember, we will be using this polynomial functions to try out different types of curves, and then finally pick up a particular curve that is very closely satisfying the pattern. So what we have next is basically, how do we calculate the curve, right. So we will basically take the use of this error function, right. So remember, the values of the coefficients will be determined by fitting the polynomial to the training data. Remember, the coefficients values are always determined whenever we have a polynomial function, right. We just saw the polynomial functions. The values of the coefficients, that is w0, w1 and so on, will be determined by using the training data only. So we will always use the training data to find out the coefficients, the value of the coefficients, right. And how do we do that? That can be done basically by minimizing an error function. So we have an error function, and we will be just describing below what is the what actually is the error function, and that will basically measure that whether the curve that the model is predicting is close to the is basically what we are expecting or not, right. So how do we use the error function? So this is the error function that we use. So we have the polynomial function that we are considering, right. For every data point we will put it into the polynomial function, and basically this is, remember, done only the training data, right. And then what we have is the target value. This is the actual value, and this is the value that the model is predicting. So the difference between them and the square for all the data points. So this is basically sum of squares. You can see this is a summation, n equal to 1 to n for all the data points. Remember, in the curve there were 10 data points, so n will be equal to 10. So for 10 data points, for each and every data point, so you can just see, I will just showing this to you. So remember, we are just using a polynomial function to basically come up with this. Just give me a minute. Yeah, so this is a polynomial function. So we will be trying different polynomial functions, and we will basically put the value of x in this function for certain coefficients, and basically that will give us the value of y x comma w. So this is nothing but the predicted value, right. This will be the predicted value, right, which the model is predicting, and we have t, which is the actual value. So we'll find out whether the difference between predicted and actual value is very minimum or not, right, because our target is that the predicted value should be very close to this actual value. Only then we can say that yes, the model is basically following the pattern, isn't it. So just again for the reference, this is the error functions that we are going to use. This half and n terms will be discussed clearly in the following slides, why we are using the half term. N is the number of data points. So for 10 data points we have the predicted value and the target value, that is the actual value, and we basically perform the difference and the square, and we will add it for all n terms, for all the n points, right? So this is the error function, remember, that we are going to use, and this is nothing but the sum of the squares of the error, a very widely used error function. We shall see in the following slides how it is actually working. So this particular curve here, suppose the data points, as usual, there are the data points 1, 2, 3 and some more data points, suppose 4, 5, 6. Let me use the blowing. Remember we had 10 data points, so I'll be using 10. So 1, 2, 3 points are already here. Suppose this is 4, this is 5, this is 6, 7, 8 is somewhere here, 9 is somewhere here, 10 somewhere here, right? Now, so we know that these data points are following certain pattern, and it is in the back of our mind, we know that these data points were generated using the sin 2 pi x function, right? Sin 2 pi x function, this was the function that was used to generate this data, a sinusoidal curve. That is the pattern it is following. But this is what we know, but we want our model to basically predict that yes, this is the pattern actually it is following, that the data points actually following. So the model for basically for using the polynomial functions will generate a curve. Suppose using the polynomial functions y and x comma w, the model basically came up with this curve. Now the model will basically justify whether this curve is the good one or not. How do you find whether this curve is a good curve or not? We basically will find out how much is the difference between the true value and the actual value in a value, right, for a data point. So there were 10 data points here, right? So suppose I consider this data point. Now this data point, what is the true value? The true value of this data point, because this is the x-axis value, right? This is the value, this is a point x. For this point x, we can see this particular value is this one, right? This is the value, isn't it? Let me make it more clear. So what does it mean? It means that this particular for x, for the value of x to be this point, suppose x0, for this point, for this value of x, the actual value is this, right? But the model basically came up with this curve. So if I find out what is the value of predicted value of x0, when you feed it in this function, you get this value, right? So what is the difference? This is the difference, right? You know that this should, for this point, the value of t should be here. This is the actual value. But if the curve passes in this way, which means that this, for this particular x value, the value of t is here, the predicted value. So is it right? No, because there is an error, isn't it? We know that the true value is this. Actually this particular point should be lying at this value of t here, but for this value of x, for this curve, it is lying at this point, which means this is the value of t. This difference is the error. Now this error exists for all the points. You can see even for this point, for this value of x, the true value of t is this one. Just extend the line from the y-axis. Here you can see this is the true value of t, but the curve passes this way. Because why does the curve passes this way? Because you used a polynomial function of certain order m with certain coefficients, and you got this curve. The model got this curve. So if the model uses this curve, then you can see that there is a difference between the true value and the actual value. For this particular point, the true value is this somewhere here, right? And this is the true value, the actual value, and the predicted value is this. The model is estimating it to be this part is the error. So likewise, you can see for all the data points, for n data points, they'll be computing the error. How do you compute the error? We just came across the formula. You find out the predicted value, you know the true value, you subtract and perform the square and add all these errors, right? This is how you compute the error, and the objective will be to reduce the error, to reduce or minimize the error. That is the objective, and that is how the curve will adjust itself to basically come up with a curve which has a minimum error. Now, so we can see the error function here corresponds to 1/2 of the sum of the squares of the displacements shown by the vertical green bars, right? So this vertical green bar is nothing but the error. This is the displacement, isn't it? Because the actually this, for this particular value of x, the true value is this one, but here you can see by using this curve, if the model uses this curve, if the model assumes that this is the pattern that the data point is following, then the value for this x here, the corresponding value will be this point. But this is not true, right? Because it is quite away from the actual value. This is the error. So we can solve the curve fitting problem by choosing the value of w for which the error is as small as possible. Remember, the error functions is in terms of w, right? So if you basically look into the error function here, if you look into the error function, if you expand this particular function, you will find out that the error function is basically nothing but in terms of w, which means if you want to minimize the error, what we need to do is basically adjust the values of the coefficients, right? So the model basically adjusts the value of the coefficients to basically come up with a curve which will very closely follow the pattern. So we can solve the curve fitting problem by using the value for w for which EW is as small as possible. Now the error function is a quadratic function of the coefficients of w, isn't it? We just saw the error function is nothing but a quadratic functions of coefficients of w, and its derivative with respect to the coefficients will be linear in the element of w. No doubt that is true, isn't it? And so when we minimize the error function, it will always have a unique solution. So hence we understood that by adjusting the values of the w, by choosing suitable values of w, we can basically by using the suitable values of w, we can come up with the curve or the polynomial function that is very closely following the pattern of the data points in the training data. Next we have, so we noted that the goal is to achieve a good generalization by making accurate predictions for new data, right? So the goal is basically to achieve good generalization by making accurate predictions for the new data. We shall see this in more detail in the following slides, what actually these things mean. Now you see, remember the polynomial functions was in terms of y, you have x comma w, and we had some polynomial function written, right? Now there was a term m, right? So remember there are 10 data points here still, and we know that the data points are actually very closely following the sin 2 pi x distribution, green curve. That is what we know. But now the red line is what the model is, or the machine is basically trying to learn, right? So the machine will basically try to learn and adjust the red line such that it will be very close to the green curve, very similar to the green curve. Only then we can say that the machine has learned the pattern. So initially the machine suppose takes m equal to 0, so which means the order of the polynomial is m equal to 0, and hence it has a curve like a straight line, right? A constant function. So do you think that this red line is very similar to the green curve? This red curve is very similar to the green curve? No, there are lots of error. You can see this is the error, because for this particular point you can see for this particular point this curve indicates that this point will lie here, but actually the point is lying here. For this particular point you can see this is the x value, so accordingly the predicted value will be this, but the actual value is this. The predicted value is this, but the actual value is this. For this curve, for this particular point, the predicted value will be this one will be same, right? And the actual value is basically this. So there are lots of error present here, right? So it is actually not at all following the pattern. What about this? For m is equal to 1, if we increase the order of the polynomial, we can see the curve has been tilted, right? And here again you can see the errors, right? How is the error present? So you can see this much is the error, right? This and basically this much is the error for this data point. For this data point again you can see this, and this much is small is the error. For these two there is very negligible error, not negligible, sorry. For this data point, suppose for this particular point, right? So x value is this, so what will be the corresponding predicted y value? Somewhere here, and actual value is this. So you can see this much is the error for this data point. What about this? The x coordinate will be this, so if it just touches the curve, this will be the predicted value, and the actual value is this, again this much small error. For this again, strike the curve, you can see at this point it is meeting the curve at this point, so this is the value of predicted value, but this is the actual value. This much difference exists here, right? Likewise you can see there are lots of errors present. What about m equal to 3? So if you see at m equal to 3, this particular red line adjusts itself, right? For m equal to 0 this was the line, for m equal to 1 this was the line, and when m equals to 2 and m equals to 3, this red line basically adjusts itself to a curve which is very closely related to this green curve, which means the machine is basically learning the pattern very well now, right? And even in this case, if we find out the error is very small, not much difference is present in the error, right? You can see for this particular point the curve is here, the predicted value is also this, the actual value is also this. For this particular point, the predicted value is at this point and the actual value is actually slightly lower than that point. And here you can see the predicted value again is equal to the actual value, which means the model is very well capturing the pattern. For this particular point, you can see the predicted value will be slightly lower here, but the actual value is slightly above. So the error is very small actually. So our target was to basically minimize the error. Minimize the error means minimize the distance of the curve from the data points, right? You can see this curve is very much distant from the data points, right? Here also you can see this curve is the red curve basically is very much distant from the data points, right? So these are the dispersion, these are the errors. And here you can see the distance between the data points and the red curve is very slight, which means very small, which means the error is decreasing. And if the error is decreasing, which means the machine is basically successful, being successful in capturing the pattern in the data. And once it captures the pattern in the data, which means the machine has understood that this particular function is being followed by this data points, and hence for any random point, again as a test data, for this particular value of x, we can very rightly predict the corresponding value of t, isn't it? And again, one thing to notice is on further increasing the value of m, that is for higher order polynomial functions, we can see that all the data points passes through the curve. That is the curve, the machine basically generates a curve which will pass through all data points, right? Which means the distance between the true value and the actual value is 0, right? That is fine. But do you think this is the pattern the machine should follow? No, right? Because this is not the curve that we used to generate the data. The curve that we used to generate the data was this green curve, and we can see for m equal to 3, this red curve is actually very similar to the green curve, although not all the points are passing through the red curve. But still this is much better than this curve. Although all the points are passing through this red curve, but this has failed to capture the actual pattern that was present between the data. Now if you rely on this particular curve, now if you say that okay, this is the correct curve, this is the curve, or this is the pattern present between the data, then for any test value of x, for this value of x, right, what is the predicted value? This is the predicted value, right? Suppose, and the line is crooked, this is the predicted value. But do you think this value is the actual value? No, this is incorrect value, isn't it? Because the predicted value should be this one, because this curve should strike at this point, right? Similarly, what about this point? For this value of x, the correct value of t should be this one, right? You can see according to this curve. But if the model uses this curve, although it is passing all through the points, and if it concludes that this is the pattern that the data is following, then, and if it chooses this curve and this as a function, then what will happen? Then for any test value of x, it will basically give a wrong prediction. So for this particular value of x, you can see this should be the wait, let me just clear this. For this particular value of x, you can see this should be the value of t, right? This one here. But what happens if you go by the red curve? If you select the red curve, then this will be the value of t, and which means there is lot of error present between your predictions and the actual value, right? Hence we can see that this case leads to overfit condition, which means if the machine basically tries to reduce the training error to zero, you can see these are the training data points, right? Here the error is 0. Why? Because you basically have the actual value and the predicted value as same. So you try to cover all the training data points, you try to come up with a curve which is basically generating 0 error for all the data points, but then you ended up coming up with a wrong curve, because that here, although the error in case of training data, you see these are the training data, right? These are the training data points. In this case the error is 0. If you compute the error, if you compute the training error, it will be 0, isn't it? Because you see for this point the actual value and the predicted value is in the same point, right? for this, like this is lying on the red curve, so the predicted value is this, actual value is also this. The predicted value is this and the actual value is also this. So with what happens, the difference is 0, and the sum of the square of the differences again is equal to 0, which means the training error is 0. But while you try to reduce the training error, you ended up increasing the testing error, because you came up with a wrong curve. For any testing point here, we just saw this should be the value of t, but you are giving this as the value of t, because this point basically meets the curve at this point. So this is the error that is present, that is a testing error. So how basically the model will try to fix this? So we'll just see that in the next slides. So we see that the root mean square error, right? So this is how this now remember the square error, EW was basically nothing but the sum of the square of the errors. Now we introduce the term root mean square error, which is nothing but we perform the root of this error. This is a significance that lies why we are performing the root. We will be discussing that in the following lectures. But yeah, this is the value. This is what the root mean square function, root mean square looks like. We have the error value. We divide it by the number of data points we are considering and multiply it by 2 and perform the root. That is the root mean square. Now what we did was basically we chose different values of m, which means we assumed different order of polynomial functions, right? We computed the training error and we also computed the testing error, right? We computed both. So how did we generate the testing points? We just use the same technique. We used the sin 2pi functions, we added some random noise and we came up with some data points in the space, and we assumed that it to be the testing data point, and we wanted to compute the error in them. So for m is equal to 0, when we have a lower order polynomial, remember the polynomial functions y, x, comma w. For a lower order polynomial, we can see the training error and the testing error is at this point, right? For m is equal to 0, we use the function to basically come up with a curve, and when we came up with a curve for m is equal to 0 and we found out the training error, it was at this point, this value, and the testing error for the same curve. Testing error in the sense when we had some, now let me just explain what is happening here. So now see how is it operating. So you remember here we have m equal to 0, m equal to 1, m equal to 3, m equal to 9. These blue points are nothing but training data. How did we compute the training data? Randomly we generated it using the function sin 2pi x, right? We use the sin 2pi x function for some values of x. We basically generated these points here, and we introduced certain noise here to make it move away from this sinusoidal curve. Now again, for generating the testing data, we are using the same function sin 2pi x, and we will add some different noise here, which means suppose the training data points will be looking like this. Suppose I'm using the suppose pink one as a testing data points. So we use the sinusoidal curve. Now suppose the testing data points are this one here, suppose this, suppose this, suppose this, suppose this, suppose this. These are the training data points. How did we generate the training data points? You can see again we use the sinusoidal functions, but with a different error rate, different noise rate, to move it away from the sinusoidal curve. Now this is a testing point. Now once you used this, now see this red line is what the model is predicting, right? Model is predicting this particular for m is equal to 0. Model found out that this is the pattern that the data is actually following. Model says that for m equal to 0, this is the pattern that the data is actually following, right? Accordingly, it will find out the training error. So training error, how will it find? Basically the difference between the predicted value and the actual value of these blue data points. So while training error, you focus on the blue points because they are the training data. What is the difference between the actual value and the predicted value? Predicted value means this is the curve that you are predicting. So this is the values, corresponding values where it is meeting in the curve. That will be the predicted values, and these are basically the actual values. And for finding the testing error, you focus on the testing points, this one. So what is the predicted value? You can see this particular point meets the curve at this point, but actually it is present at this point. So this is the error in this testing data point. For this testing data point, it is meeting the curve at this point, but it is actually present at this point. So this is the testing error. So add them, square them as we discussed in the error function. That will give you the testing error. So you will perform the same for all the different values of m. Once you do that, we are basically performing an analysis, nothing else. So we are just performing an analysis that The graph of the root mean square error evaluated on the training set and on an independent test set. Remember how we generate the test set and training set for various values of m. M is nothing but the degree of the polynomial, order of the polynomial. So for m is equal to 0, we find out the training error to be this value. This is the value. Test was this one. For m equal to 1, again this was the training error, this was the test error, which is slightly lower than the what was in m equal to 0. M equal to 2, again this was the training error, this was the testing error. We can see at m equal to 3 the training error is minimum and the testing error is also minimum, right? Isn't it? You can see at m equal to 3, which means when you have the order of polynomial m equal to 3, the training error is very small, minimum, isn't it? It reduced because at m equal to 0 the training error was very close to 0.5, but at m equal to 3 it is very close to 0, and testing error is also close. For certain values of m in a certain range, it was basically almost consistent, right? Less. But again, when we saw that when the order of the polynomial, that is m, when the value of m increases beyond a certain point, when it increases, which means that what happens, the training error, you can see here, reduced to 0. The training error reduced to 0. Why? When for higher order polynomial, the curve tries to pass through all the training data points, and if the curve tries to pass through all the training data points, right, then what happens, the training error will become 0. But that was not the curve that we are expecting, right? It led to overfit. Hence in overfit, what did we see? The testing error is very high, right? So we can see a very closely relate this with this curve. Yeah, this was the curve that we are using. See, for m equal to 9, what happened? For m equal to 9, it was passing through all the training data points, and if you compute the training error here, which is nothing but predicted value minus actual value, which is t, and this predicted value is nothing but a function of yx comma w square, you see the training error will be equal to 0, because you see your curve is actually passing through all the data points. The true value and the actual value are same, but this is not the actual curve because it led to overfit. And if you have some test values, if you are generating some test values, for them the error will be very high, right? So this is the overfitting condition. For m equal to 3, you can see what did we see here in the next slide. What did we see? For m equal to 3, you can see the error was very less, the training error was very less, the testing error was also very less, and it is obvious it has to be less. Why? Because the curve that we predicted was very close to the curve that the model had predicted was very close to the actual distribution of the data. Hence it is obvious that the training error and the testing error both will be less. So if you have some testing values here, then whatever output this curve will generate will be very much more good and proper as compared to these other predictions, these are the patterns that it observed, which means we can conclude that the model had predicted the correct pattern for m equal to 3, the correct curve it has predicted for m equal to 3, isn't it? And these higher order values of m led to overfitting. So we can see this is m equal to 0, you will have 1 coefficient, m equal to 1 you will have 2 coefficients, m equal to 6 you will have 4 coefficients. So we can gain some insights into the problem by examining the value of the coefficients w star obtained from polynomials of various order, right? So we see that as the value of the m increases, which means for higher order polynomials the magnitude of the coefficients typically gets larger, either more positive or more negative. You can see for m equal to 9, this was nothing but an overfit condition. What was it? Overfit condition. What was happening here? The curve was passing, the model was coming up with a curve which was passing through all the training data points. Hence in that case the training error was becoming 0, but yes, in that process it lost the generalistic property and the testing error was very high because that was not the pattern that the data was actually following. So you can see for higher orders what is happening, overfitting is happening. Why? Because of higher coefficient values. The coefficient values are very high, you can see. This is leading to overfitting, right? So any process how we can handle this overfitting? Yes, there are techniques of handling overfitting. You can see for m is equal to 9. For m equal to 9, the curve was very messy, isn't it? So let me just show you. Just remember this curve. Just remember this curve for m equal to 9. You can see this is how the curve actually looks, quite away from the original distribution. Means that there is a very big difference between the red curve and the green curve, right? If the red curve is very close to green curve, it is correct, means it is a good pattern that it is observing. But here the red curve is very much away from the green curve, right? Not quite similar. So now if you focus on this m equal to 9 and we try to basically optimize the values of weights W coefficients and basically try to give proper shape to this curve. How do we give proper shape to this curve? By adjusting the values of coefficients W, right, and basically trying to reduce the error. We will be trying to basically reduce the error. If there is a big difference between this, you can see there is a big difference between this, right, there's a difference between this 2 point and the actual true value, actual value. So we'll try to come up with a curve such that this error is very low. So they basically tried to perform this, and what they came up with was, you can see what they did was, initially they had n equal to 10 data points. They then increased the data points n equal to 15, which means by increasing the number of data points in the training set, by increasing the training set data points, there was slight improvement in the curve. The curve was actually trying to, it was highly oscillating initially when we had 10 data points, but now you can see it has basically tried to reduce the number of oscillations and it is trying to come closer to the green curve, to look very similar to the green curve. But if you increase n equal to 15 to n equal to 100, if you have more number of training data points, you can see a shocking result, which is that the green curve, that the red curve, which means the machine comes up with a pattern which is very close to the green curve, which means the machine is actually learning the pattern when we have more number of points in the training data set, isn't it? You can see this diagram, the graph is itself evident of the fact. When we had n equal to 10, there was very large number of oscillation. For n equal to 15, which means 15 data points, the curve that we are coming up with was very close, was trying to come up closer to the green curve. But if you increase the number of data points to 100, the curve that it comes up is, very much similar to the green curve, Hence we can say the machine has learned very well here. So if you have large number of data points, you can basically, now if the machine has learned very well here, which means it has reduced the overfitting, isn't it? So you can see increasing the number of data points can also play a crucial role in controlling overfitting. Another thing that we can do is basically regularization. We can also perform regularization. You can see we'll be coming up with the regularization concept in the following slides, but I hope the concept of polynomial curve fitting is clear, how the machine actually tries to fit itself to the curve. We'll be discussing more concepts about polynomial curve fitting in the next slides. So that's all from this particular video. I hope this video was helpful. I know it was lengthy, but my objective was to make things crystal and clear. Thank you for watching.